Greetings and welcome to Calculus 3. Today we're going to be talking about the three-dimensional coordinate system. It's going to be a brief introduction to the three-dimensional system, and mainly because we're going to be going into multivariable calculus, and while we're all familiar with the two-dimensional coordinate system, we may not all be familiar with the three-dimensional coordinate system. But even if you are, it should be relatively quick and give you a nice refresher. So just like in a two-dimensional system, we can represent the three-dimensional coordinate system with axes. So I'm going to draw a three-dimensional system here, and there's a variety of ways that this can be done. I'm going to draw mine like this here, and then to show the three-dimensionality of it, we draw this diagonal line in like this here. Okay, so now how do we label these pieces? Customarily, we generally label this axis right here as y, this axis, this angular axis, as x, and then this axis up here as z. And you can see that this kind of breaks up the surface, the space. There we go. Breaks up the space into different what we call octants, not quadrants. Quadrants are for the two-dimensional space, but this is for octants. The positive directions here, so this is y positive this way, up is z positive, and then out of the page would be x positive. And so then that makes that this section right here, if we kind of think about, you know, the planes, the xz and xy and zy planes, these planes right here all enclose what's called the first octant. So, and that's really what we're going to be worried about. We can go into other octants, but we really are only going to really name the first one. So the first octant, and that's where x is greater than 0, y is greater than 0, and z is greater than 0. All right, so now the other thing that we're going to talk about is, how do we know that this is, this is x, positive x, this is positive y, and this is positive z? Well, it's just a standard that we use, and the thing that we could, that we rely on to keep us all on the same page is something called the right-hand rule. And you'll find pictures of these in textbooks and things like that. But basically the idea is that you wrap your hand around the z-axis. So you take your hand and you wrap it around the z-axis. You take your right hand and wrap it around the z-axis. And then if you point your index finger, then that is going to go the same way as the x-axis. And then the other three fingers are going to actually point along the y-axis, along the positive y-axis. And then your thumb, must forgive me, I'm not very good at arting yet. So there's a thumb. Oh, this guy's got a broken hand. Okay, so the thumb is going to point in the positive z direction. So that's the right hand rule. It's more important in engineering and physics, but if you ever want to know which way the x and the y and the z axis should be pointing, you wrap your hand, your right hand, around the z-axis, and then point your index finger along one of the axes, and then the other one will be the positive y-axis. So write this up real fast. Okay, up right hand around z, and look at your index and other fingers. Okay. All right, so that's all nice and good. So now what? So now we're going to talk about projection. When we have a point in three-dimensional space, we can talk about what it looks like on each of the coordinate planes. So I'm going to get another coordinate plane set up here. My X, or that's my Z, and then here's my Y, and then here's my X. So now when we want to talk about points in the coordinate plane, a point in R3, if you're not familiar with that terminology, the R here just represents the real numbers, and then the 3 tells us how many dimensions we're in. So like the XY coordinate plane would be R2, and this is R3 because we've got 3 coordinate planes, or 3 coordinate axes. So give that a Y, give that an X, and give that a Z. Okay, so a point in R3 is labeled like this. It's how far from the origin in the X direction, how far from the origin in the Y direction, and how far from the origin in the Z direction. So if I take, I can take a specific point. Let's take the point 2, 5, 3. All right, so then put on our hash marks here. And you can make these as pretty as you want here. So to get to 0.253, we're going to come out to 2 on the x-axis, and then we're going to march out 3 on the y-axis. Sorry, we're going to march out 5 on the y-axis. So you can imagine if you followed this hash mark perpendicular to the x-axis, then where the line coming out perpendicular from the x-axis, the line that's parallel to the x-axis coming out from that hash mark meets up with the line that's parallel to the y-axis coming out from x equals 2, that's where that point's going to be. And then we're going to go up 3 units. So imagine 1, 2, 3. So I'm going to kind of do the same spacing here. Okay. So there's the point 253. All right, so now we can imagine that if we had a coordinate plane, maybe I don't want a square here. Let's see if we can do a rhombus. Okay, so we've got this rhombus here, and it may not do what we want it to do. That's okay. Well, I'll just free-form it here. Okay, so you can imagine that we've got there we go. Okay, so we've got this coordinate plane here. So this right here, what I'm coloring here is this is the XZ plane. And then you can imagine over here we've got the YZ plane. and then the floor of our octant is the xy plane. Okay, so what we want to know is, well, where does this point project onto various planes? So we could ask, where does 253 project onto the xz plane? So one of the things you can think about, well, look at the xz plane. The xz plane is where y is equal to 0. And so if we take this point and we march it back, what we're doing is we're marching it back along the y-axis until y is equal to 0. So where does 253 project on the xz plane? It projects to the point 2, 0, 3, where y is equal to 0. And then we can ask another question. We can say, well, where does it project onto the yz plane? And it's kind of the same idea. So you're going to take that point, and then if you look at the yz plane has the x value is equal to 0. So if I take this and march it back, what I'm doing is marching the x value back to 0. And so the points on the yz plane is going to be 0 for x, but then the y and the z value stay the same. So not too shabby, nice and easy. All right, so now let's talk about what a graph looks like, or what a surface looks like. So in a three-dimensional space, you can graph a variety of geometrical shapes. I mean, obviously, in a two-dimensional plane, you could graph. Well, what could you graph? You could graph a point, right? Do it like this. Graph's possible. There we go. Okay, so you could graph a point, you could graph a line, and you could graph a curve. And you could also, you can start to get creative. You can also graph plane shapes, flat shapes. But you couldn't do anything more than that, because a shape takes up two dimensions. So what about in 3D? Well, in 3D, now, in R3, the graph's possible. All you do is you add surfaces and volumes. So we're going to add surfaces and volumes. That's really, the thing we're really going to explore over the next several sections is how this works, how calculus and math works in three-dimensional space. Okay, so let's take a look at what this means if we've got if we're talking about three-dimensional graphs. Can we have a point? Can we have a line? Can we have a curve? And yes, all those things are possible. And then we have these really cool surfaces that we can make. So let's consider. So one question we can ask is, what is x squared plus y squared is equal to 4 in R3? So in R3, or in R2, we would know what this is. This is just a circle whose center is at 0, 0, and whose radius is 2. Now in R3, z's not in this. And so that means that this is a cylinder of radius 2, who's centered at 0, 0. because there is no z to restrict it. So if we were to graph it out, let me do this quickly. So if we were to graph this out, we would have this circle of radius 2 here. There we go. But since there's no z restriction, then it would go up and down. So this would be like a pipe going up and down. It wouldn't stop here, it would keep on going. So if you're missing a variable in your equation, in your relation, then that means that particular variable is free. It can be whatever it wants. If we were told that z was between something or z was equal to something, then that would change what we were dealing with. So this is an infinite cylinder. Centered at 0, 0. Or 0, 0, 0, centered at the origin. And has radius 2. Okay, so now let's consider this. So I look at the same thing. X squared plus y squared equals 4, but then I'm also going to give a restriction on z. So we're going to say that z is between 0 and 3. And I'm even going to go ahead and say that this is x squared plus y squared is less than or equal to 4. So this now, what this is this is a filled cylinder This is a filled cylinder of radius 2. Three high, centered at the origin. So if we were to put this on this shape here, we could come up, 1, 2, 3 right here, and then we have this circle there. I will get better at this, promise. Okay, so we've got the circle, it's filled in, and then this whole volume underneath it is filled in as well. Okay, so it's going to be a variety of problems that talk about surfaces in the book, in the homework, and the big thing to remember there is if the one variable is not mentioned or two variables are not mentioned, then those are free, and those can be anything at all. All right, now on to a little bit of math. So in the two-dimensional coordinate system, we have the distance formula. So in R2, the distance between 2 points is, we should all know this from pre-calculus or algebra. So between x1 and y1 and x2, y2 is d equals the square root of, well, it's just the difference between the two x and y values. So we've got x2 minus x1 squared plus y2 minus y1 squared. Okay, so now how do we expand this out to the third dimension? I'm going to give you the formula. There is a nice little proof that goes along with it, but for the sake of time, we won't worry about that. So in R3, the distance between now we're going to have three coordinates here, x1, y1, z1, and x2, y2, z2. Okay. And that is just going to be equal to the square root of, and it's just the sum of the difference of squares between each coordinate. So x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Okay, so it's very similar to what we would expect it to be. Now, one of the things that you learn in algebra is that if you square the distance formula, you get a circle, right? And the same thing kind of in R3. If you square the distance formula in R3, you get a circle essentially in 3 dimensions, which is a sphere. And we're going to call that the equation of the sphere, and it's a very useful equation. That's about what you would expect it to be. I'm going to change the letters around a little bit here. So we're going to have an equation of the sphere of radius r centered at, there's a variety of centers. I think we're going to use we're going to use H, K, and L. There are certain books that use it like that. All right, so the equation of the sphere of radius r centered at H, K, and L looks just like the equation for a circle. So r squared is equal to x minus h squared plus y minus k squared plus z minus l squared. And that's it. And so we're going to do a couple of problems here, and one of them will involve prepping a three-dimensional equation, three-dimensional relation, and turning it into an equation of a sphere. So cover that in a second. The next thing I wanted to show was the equation of a cylinder. And the equation of a cylinder, we've seen it already. So, equation of a cylinder, we're going to talk about, and we've got to be able to make a circle, and then we've got to be able to, we could limit it if we needed to. So, the equation of a circle of radius r and centered. Well, and centered is really kind of a strange term to use here, because we're centering in terms of a plane. So we are going to we're going to talk about it being centered, but the one of the values isn't well, yeah, it's going to be a little strange, but let's just write it down like this. So it's going to be centered at H, K, and L again. So this now it's going to look like this. So this is going to be perpendicular to the XY plane. So that's going to be x squared, or x minus h squared plus y minus k squared equals r squared. Like I said, you'll notice I didn't use L at all, because for a cylinder, one of the variables has to be free. You can restrict it between something, but the other variable will not show up in the equation. And so if you wanted to do perpendicular to the YZ plane, then it would be very similar. I can go ahead and do it here real fast. So if we did perpendicular to the YZ plane, so just like up here when it's perpendicular to the XY plane, the X and Y were included. Perpendicular to Y and Z, it means that Y and Z are going to be included. So it's going to be Y minus K squared plus Z minus L squared equals R squared. All right, so let's do some problems quickly here. The problems in this are fairly straightforward in this section, and some of them are a little bit interesting. So if we have